In this video, we're going to go ahead and take a look. How's it going, everybody? In this video, we're going to go ahead and take a look at verifying some of the outputs that we saw in the previous video. We're going to take a little bit of a deeper dive into the how do you verify things are working and stuff like that. So let's go ahead and dive into the specifics. I'm going to go ahead and I've actually got a couple things pre-staged already just so we can go through them. And so let me go ahead and hit the enter key a little bit just so I can refresh the timer. So we're going to look at this and break down some of the details here so you guys understand what you're looking at. So as we start looking at the EIGRP neighbors detail, we need to understand some of the outputs. So going from left to right, so we're going to go this direction. We have, at the very top, we have H. I don't really know what that stands for. I've done some research to try to figure it out. There's no real detail. I even spoke to one of the people that actually helped develop EIGRP. His name is Donnie Savage. Super nice guy. He's devious on Twitter. That's just public knowledge for those people that are familiar with him. I asked him, and he kind of looked at me and says, "Because that's just what it is, Rob." And I go, "Fair enough." So yeah, there's that. So we have that. We have the address. The address is going to be the next hop IP, or the IP address of the interface that we're peered with. Okay, so that's going to be where the source or the destination IP address we send any of our updates. The interface is going to be the interface in which that adjacency happens to be peered to. So in this case here, 100.1.3.3 is we can reach them out gig 0/0. Pretty straightforward stuff. Now the hold time here in seconds is the hold timer of the neighbor. So in this case here, we're sending the information back and forth. Now remember, the hold time is not dependent on being operational, meaning we don't have to agree upon it. I shouldn't say it doesn't need to be operational. We just don't need to agree upon it between the neighbors. So for example, if R1 is 5 and 12 and R2 is 6 and 17, then which don't actually add up correctly, but for example purposes, then they would need to match up, or OSPF they would. Let me back this up just a little bit. We have the uptime, which is how long the adjacency has been up. So right now it's sitting at 25 minutes. The smooth round trip time, or SRTT, is the time in which a RTP, the reliable transport packet, takes to go out and then come back in. Okay, that's how long that timer is. The round trip timeout, or RTO, is the amount of time that the router will wait to retransmit the EIGRP reliable packet if an acknowledgement is not received. Okay, so keep that in mind. That's RTO. The queue count is the number of updates, queries, replies, etc. of EIGRP packets that is waiting to be sent. Right now is 0. This is what you want it to be. If it's anything other than 0, there's a problem. And the sequence number is the last packet being received from the neighbor. Excuse me, I had to think about that for a moment. Basically, this is just to ensure that the neighbor is receiving the packets received from the neighbor. Just make sure that they're being received in order. So there's that. So these are just some of the variables that come into play. And if you look right here, we can see that we've received prefixes of 9. We can see that we've received prefixes of 7. So when we look at those details, we can see that what we've learned and all that type of stuff. Topology IDs from peer is 0, which means we're not doing any type of multi-topology configuration. We're not doing anything there. And topologies advertised to peer is base. So you have a number of different topologies that you can leverage. So you have base, which is basically going to be the default VRF. And then you can get into other VRFs that you can create to do multi-VRF routing, separate staff from faculty, from student, from whoever else might be on in a college or a university type of infrastructure. That's something you could deploy there. So there's that. We have no neighbors, considering we aren't doing any type of unicast connectivity or anything like that. So let's go ahead and take a look at our next variation of this. I'm going to go ahead and hit the up arrow, and we're going to look at a specific output. We go ahead and scoot this up to the top a little bit so we can see what's going on. So this is an output of a neighbor statement from the topology table. We can see that we're receiving traffic in from AS100. This is the my local loopback address, and this is the information I received from 100.1.0.5. So specifically from the loopback address of iOS 5. We can see the state is passive, which is good because then we know that nothing is going on. The query origin flag is 1. The successors is 2 because we have two different ways of getting there. We can go either towards XR2 or towards XR3. And the feasible distance, which is our composite metric, is 131,328. So there's that. So we're in good shape in that particular case. Now if we come down here, we can see who our neighbor is and the interface we're going to use to reach them, the IP address that we're going to use to get there. The send flag is basically null. We're not sending anything. The composite metric is 131,328, and we have this value here, 131,072. So basically this right here, the 131,328 and the 131,072. This right here is going to be what we refer to as the feasible distance, and this is going to be our reported distance. And there's going to be another one here called the local distance. So this, I believe, is going to be 256, but don't quote me on that. Let me go ahead and pull up a calculator real quick. Calculator. Calculator's right there. We're going to take 131,328. I don't know how long it was not recording for. So we have 256. So let me back this up a little bit here, just so everybody's on the same page. So what that comes into play, and actually let me minimize this real quick, and clear the screen, and bring this over just a little bit so you guys can see what I'm talking about. So when we talk about this, you take that 131,328, subtract that from 131,072, you get 256. That means from here to here and from here to here, the cost is 256. And then from here to here and from here to here is whatever this this remaining value, 131,072. Okay, so this is the local distance. This is the reported distance. This is the feasible distance. So you always take your local distance and your reported distance, you glue those two together, that becomes your feasible distance. Okay, just so everybody's on the same page with that. Now as we continue going further down, you can see the route is internal, which means it was not learned from any other routing protocol other than EIGRP. We can see the vector metric because it is a distance vector routing protocol. The minimum bandwidth is, we got 1, 2, 3, 4, 5, 6, so it's one gigabit per second. 1 gigabit per second. So basically a million kilobits is that value. The total delay for this interface right here is going to be 5,030 microseconds. And then that and this, so delay and bandwidth, come into play in terms of how we determine where we're going to send traffic. So we're going to play around with these variables when we get a little bit further along, but this basically is what is being used in order to determine how we forward traffic. So these are the variables. Now you'll notice that reliability is 255, so it's very, very reliable. It's the maximum reliability. We have the lowest load, and the minimum MTU is 1500. Now if the MTU could be higher, so like 9216 or something other than that, then you could bump that up, which would allow you to send basically larger payloads every sending increment. But right now we're not doing that. Now you notice that it says minimum bandwidth. Minimum bandwidth means that the minimum bandwidth between the source and the destination right now is 1 gigabit per second. Now if I wanted to bump that up to be some sort of higher value, so if I wanted to say it's 10 gigabit per second, I could go in there and adjust that value if I wanted to. However, if I do that, then I might give an improper calculation to EIGRP, which might cause EIGRP to work ineffectively. So I definitely don't want to do that or mess things up in terms of how EIGRP works. When we look at the hop count, we can see it is 3 hops away. So the way we calculate hops is we always calculate it from the next device from us is always the first hop. So in this case here it would be 1, 2, 3. And this particular path, right? We come over here, we have 1, 2, 3. And then from this one here again will be 1, 2, 3. Right, so we have 3 total paths. So let's go ahead and draw these out. So we have and we don't know which one we're going to choose, right? We could use a number of different paths. So we'll say we have this first path right here, right? We have this path right here. That's the first one. Then this other one, we're going to go to sky blue. We have this guy right here, this path. And then the third path will go orange is this one. Oops. Like so. So we have 3 different ways to get to router 5's loopback. Great. That gives us that many more opportunities in order to reach our destination, which means that we have 3 possible ways in order to get there. Initially, we only have 2 because router 1 only has 1 link to each next hop router. So, which means that when we get to iOS 4, we technically have additional paths beyond that. We could actually have let's go brown. When we get to down here to router 2 or router 4, we can go this way, then we can go down this way, we can come back this direction. So we technically have a 4th path as well. But that's reliant upon this connection here between iOS 4 and XR3 being up and running. But if this guy went down, we could take this alternative path if we needed to. So we have a total of 4 ways to get to where we need to go. But from router 1's perspective, he's just like, I only have 2. So right now we have, let's just draw this out for simplicity. We have this path and we have this path. We don't know if XR3 is going to take into consider this path either, but he probably will. So if we're not sure, let's go jump over to XR3 and actually look. We're going to hit the enter key here, log in, and we'll do a show EIGRP topology for 100.1.0.5/32. And it's going to say, yep, I have 2 different ways to get there. And notice that the values here are much different. Now, the reason why we see much different values is because iOS 1, iOS 4, iOS 5, and iOS 6 are all using the old school way of doing path determination. So we're using the classic mode of EIGRP. We haven't talked about named mode yet, but on XR we have enabled named mode, which means that the way that EIGRP is calculated is different. It actually uses, instead of microseconds to do the calculation, it uses picoseconds, which gives you a much tighter refresh window, but it also gives us much more granularity to use higher speed links. So for example, if you're stuck at gigabit with microseconds, you're stuck at gigabit. But if you implement microseconds, you can go to several terabits of throughput, which gives you lots and lots of high speed growth. So right now we're sitting at between 100 and 200 gigabits per second as an interface speed. I know that there's talk of 400 gigabit, but I personally haven't seen any. But picoseconds would allow us to scale beyond where we're at now. Microseconds kind of limits us to where we're at currently. So that's where that comes into play. So that's where that's at. That's why you see these outputs here. That's why we see such high variables on the iOS side. So, but for right now, it's doing what we needed to do, and there's nothing wrong with that. Just some things to keep in the back of your mind in terms of the operations. So that, ladies and gentlemen, is pretty much what I wanted to go over in this video in terms of how to interpret some of the outputs and to dive into some of the details. We don't really need to configure anything because it's already up and running, but being able to understand the outputs, most people are going to want to understand how do I verify it? It's great to know how to configure, but at the end of the day, there's only a handful of things to configure with EIGRP. And if you are not sure what I mean by that, let's go back to router 1 and go to global config and type in router EIGRP 100 and hit the question mark. There's really not a lot here. When you break it down to brass tacks, there's only a handful of commands to use, right? We're going to take a look at the majority of these, but there's really not a lot. Now, if I was to exit out, type in router OSPF1 and do a question mark, there's a bunch of additional features that we'll take a look at, which is why we'll take a look at OSPF at a later point in time and dive into those details. But right now, EIGRP doesn't have as many nerd knobs to turn, so it doesn't take as long to go through. But we'll take a look at those details. It's really, really important, though, to be able to break down what's happening operationally. So if you're presented with when you're studying for your CCNP and you're looking at the protocol and you're looking at the outputs and you don't know what you're looking at, that's why I'm trying to be as thorough as I can. Show IP, EIGRP, and you have not a lot of them, but if you look at the interfaces, for example, gig 0/0, we look at the output. If we look at the detail, we can see where's the detail gig 0/0 there. So this is just another output we can look at, and we're going to take a look at this is a lot of the same stuff, but we can look at things at the interface level specifically and take a look at timer values. We can see that the display horizon is enabled and a lot of just reference information. But it's one of those things that as you're going through, we have a base setup, right? Nothing fancy. Any CCNA at this point should be able to deploy EIGRP to the level that we've deployed it. Where we're taking it to the next level with more of the professional level, the CCNP for ENCOR and ENARSI, is looking at the details and looking into the specifics. Like, okay, how do you know that's actually working? So verifying is just as important, because when you get a question on the exam and it shows you what I'm showing you here and you're like, I've never seen that before. Well, number one, shame on you for never having seen it. I'm trying to show you as many things as I can. So I'm going to continue to try to do that as we move forward. So it's all about verifying what's going on, so you're not like, I've never seen that before. Now you have. I'm hoping that that's something that you'll see moving forward, and you'll be like, oh, I remember seeing this in Rob's video. You're welcome. So that's basically where we're at in terms of that. So that's verifying EIGRP. So let's just recap real quick some of the minimums that I would recommend you have. Show IP EIGRP interfaces. So that's going to show you what interfaces are enabled for EIGRP. You'll notice that peers shows up on some of them, meaning who we've actually formed a peering with. If I do a show IP EIGRP neighbors, that takes it a step further. So who am I connected to? In this case here, XR2 and XR3. If I look at what I've learned from those peers, I can look at the topology database. I can see what's going on in here. If I want to dig into a specific route that I've learned from one of those peers, I can do that as well. So I can come in here and type in 100.1.0.4/32, and I can look at the details. That's what we were looking at here. Now that I've looked at all that, I've looked at what interfaces are enabled for EIGRP, who I'm peered with via EIGRP, what I've learned from those peers that's installed into my topology table, and then lastly, I can do a show IP route EIGRP, what routes have been entered into my routing table. So just a real quick clarification in terms of how that works. We have our enabled interfaces, right? The first real table is going to be the neighbor table, which is going to be the show IP EIGRP neighbors, so neighbor table. Then we have our topology table, so topo table. What did we learn from those neighbors? And then we have our routing table. And they are populated 1, 2, 3. Technically this is 1, but we'll give this one 0.5 for good measure. So you have to enable EIGRP in the interface first in order for it to discover and form an adjacency. Number 2 is you have to exchange routes with that neighbor, whoever that might be, and you don't necessarily indiscriminately advertise neighbors, but you still are going to advertise, right? It's going to happen. Then number 3, you run dual, and then those best routes get injected into the routing table, and then the routing table downloads into the forwarding table. The forwarding table is what and how the router determines how to forward traffic. So think of it like GPS. Like, I know I need to get to a particular destination, right? So the neighbor table is basically going to be all the roads that get you from point A to point B, right? The topology table is when you plug in an address and you hit the direction, and the direction says, the little blue line, if you're like me, I use Google Maps, it pops up and it says take this path, and if you hit start, then it puts your car on the road, and next thing you know, in the routing table, it's got you a direct path. And that's where all these tables come into play to help you get from point A to point B effectively. I don't know about you, but I've been teaching the kids how to use GPS so that they know how to get from point A to point B. Is it foolproof? No. Does it have flaws? Yes. Is it pretty accurate most of the time? Yes, I would agree with that. But understanding how these pieces and parts come into play, that's really, really important. That's really what I really want to try to get across to all of you in this video. So, if you guys have any questions or anything, please leave a comment in the comment section below. Please like, share, and subscribe, and I'll see all of you in the next video. Until next time, guys, take it easy.